Section 13.3, the fundamental theorem of line integrals, video 4. In the previous video, we discovered that independence of path implied that the line integral over a closed curve, for a closed curve C, independence of path implied that the line integral over a closed curve was equal to 0. But does this implication go both ways? Is this a two-way implication? In other words, does this statement, the line integral equal to 0 for any closed C, does this imply path independence? In math and in logic, more in general, you have to be very careful to assume that a conditional is a biconditional. In other words, if you have a statement that says if A happens, then B happens, you can't just automatically assume that if B happens, then A happens. When it does go in both directions, it's called a biconditional, but you can't always just assume that implication in one direction always means an implication in the other direction. I'd like to try to prove this. By the way, the answer is yes, it is a two-way implication. But let's see if we can prove it. So let's suppose that the line integral over C of f dot dr is equal to 0 for any closed curve C. Now, how do we prove path independence? Well, we have to pick 2 points at random, pick 2 random paths and show that their integrals are equal. So let's pick 2 points. We'll call them capital A and B. And 2 paths. We'll call them C1 and C2, connecting them. So let's draw a picture. Here's point A, here's point B, here's path C1, and here's path C2. Remember, the paths don't have to be smooth, they just have to be piecewise smooth, which basically means you can have a finite number of sharp corners. All right, so if C1 goes in this direction from A to B, and then C2 goes in the same direction from A to B, can we show that the line integral over both of those paths will be equal? Even though we haven't defined the paths, we just defined their beginning, their initial, and their terminal points. Well, in order to prove something that you don't know, you have to connect it to something that you do know, or something that you assume in a problem, or suppose in a problem. And the supposition that we're making here is that the line integral over any closed curve is equal to 0. So somehow we have to take these 2 paths from A to B and view them as a single closed curve. And I think some of you might be seeing the trick. The trick is, if we want a closed curve, we need one path that ends where it begins. So we can use the same trick we did before, where we reverse the orientation of a path. Let's keep C1 in the same orientation as it was. Let's redefine the orientation along the second path in the reverse direction. And so that path would be negative C2, because it's C2, it's just in the opposite direction. And let's let C be C1 union negative C2, meaning that we just join them together. So go this path and then keep going. That's a closed curve. So for our proof, we need to actually state that as part of it. Let's let path C be the union of C1 and the negative of path C2. Then C is a closed curve, because it ends where it begins. And what are we supposing about closed curves? Their line integral is equal to 0. So 0 is equal to the line integral over path C dr. But we know that the line integral over a path can be written as the sum of the line integrals over the individual paths whose union makes the original path. So in other words, this line integral is equal to the integral of C1, or the integral over the path C1 of f dot dr, plus the integral over the path negative C2, remember we had to change its orientation to make it a closed path, of f dot dr. But as in the previous video, we know that when we change the orientation of a path, we change the sign of its line integral. So if we leave the first line integral alone, change the orientation of this back to C2, which will change the sign of its integral. We get that the integral over the path C1 minus the integral over the path C2 is equal to 0. 0 equals this difference. And the only way you can subtract two things and get 0 is if those two things are equal. Therefore, we can conclude that the line integral over the first path, f dot dr, is equal to the line integral over the second path of f dot dr. And therefore, we can conclude path independence, because the integrals were equal regardless of their paths as long as they had the same initial and terminal points. So the answer to it is the implication two ways. Yes, the line integral is path independent if and only if the line integral over any closed curve is always equal to 0. So if we know that the line integral over a closed curve is always 0, we get path independence. And if we have path independence, then we get the line integral over any closed curve is always equal to 0. Now in your textbook, this is summarized in Theorem 3 on page 775. I'm not going to write it on the board because it basically says what I just told you. But we need to tie this back to the problem that we had at the beginning. Remember that the fundamental theorem of line integrals says that the integral of a gradient is easy to calculate, just like you do regular definite integrals and antiderivatives. But how can we tell if the integrand is the gradient of something? Well, we'll take a look at that in the next video.